This is lesson 10.1, lines and segments that intersect circles. So we're now going to be talking about circles. A circle is the set of points equidistant or equally distant from a given point, which we call the center. So the center of the circle is how we name the circle. So this would be called circle C. And the circle itself is every point, basically the edge here, that's the same distance away from that point C. The radius is a line segment with endpoints at the center and on the edge. So the radius will be the same no matter where I draw it from the center because it's equidistant from the edge of the circle at all places. A chord is a segment with endpoints on the circle. So as long as it starts at one side of the circle and ends at another point on the circle, that's a chord. The special kind of chord that happens to go through the center is called the diameter. Now we have three new terms because you've probably seen the previous ones. A secant is a line, ray, or segment that intersects a circle in exactly two places. The difference between the secant and a chord is that the secant also has parts that exist outside of the circle. So here we see line AB is a secant. It could have been a segment A to say like a point over here D, as long as there was a parts contained inside and parts contained outside, that would be a secant line. A tangent is a line, ray, or segment that intersects the circle in exactly one place. And we call the place where it intersects the circle the point of tangency. That is the point at which the tangent intersects the circle. For example 1, we're going to tell whether the line, ray, or segment is best described as a radius, chord, diameter, secant, or tangent. So the first one is AC. So we're going from A to C. So that's center to the edge. We would call that a radius. For part B, we're going all the way from A to B. So we're going all the way across the circle, endpoints on both sides, which makes it a chord, and it went through the center, which elevates it to diameter. Ray DE. So ray DE only touched the circle at one spot, so that would be a tangent. And then line AE. Line AE has parts both inside and outside the circle, and it touches it in two different places, so that would be a secant. Here's a check-in for you to try. You can pause. Answers are posted on Google Classroom. All right, example number 2. Give an example of each segment, or point, I should say, or line, using the circle. So the center is that middle part, we would say K. A radius, anything from K to any point on the circle would be considered a radius. So there are 3 different options in this picture. We'll just name one of them. We could say like KL is a radius. A chord has to start and stop on the circle. So I could say this one here, starting and stopping on the circle would be segment HI. I could have also said segment JI, or I could have said segment JL. As long as I used the segment symbol, that would be considered a chord. The diameter. So this one has to pass through the center, and it has to reach both sides. So through the center went to L, but there was nothing past it, so we would have to use JI as our diameter. A secant intersects the circle twice and has parts both inside and outside. So the easiest one to spot here is this line JL because it has arrows on both ends and it goes forever outside the circle. But an acceptable answer also could have been GI. Segment GI is also a secant because it has parts both inside and outside the circle. The tangent, so there's only one line that touches the circle at only one point. So this line right here, or really this segment right here, is the only one that just grazes the circle. So that's segment GJ. And the place where it touches the circle was at point J. Here's a check-in for you to try. Pause. Answers are posted on Google Classroom. So a property of tangent lines, which we just said that tangent lines intersect the circle at exactly one point, is that the line is tangent to a circle if and only if it is perpendicular to a radius drawn to the point of tangency. So if a line is tangent to a circle, there will be a right angle at the point of tangency. So one thing we can do is determine whether or not a line is tangent by determining whether or not there's a right angle. And when we have a picture that looks like this, to tell if there was a right angle in this spot, we're going to check to see if we had a right triangle. And we could do that using the converse of the Pythagorean theorem. We're going to check if c squared is blank to a squared plus b squared. If it's equal, it's yes. If it's not equal, it's no. So the side across from where the right angle would be is my c value, but this 2 only belonged outside. So I need to know how long all of CE is. Since CD was a radius and that was 3, C to this spot would also be a radius, so that's also 3, telling me this whole side is 3 plus 2, or 5. So we're going to use 5 squared is blank. To my other two sides are 3 and 4. So that's 25 is blank to 9 plus 16, which is 25. So these are in fact equal. So there was a right angle there. So yes, it is tangent. And I just realized our directions are a little off. It should say is DE tangent to circle C. Sorry about that. And this has the opposite directions. So here we're going to check is ST tangent to circle P. You could pause. Answers are posted on Google Classroom. Example 4. So in the diagram, point J is a point of tangency, which means there is a right angle at J. We want to find X. So this will just do the Pythagorean theorem. This side is my C. These are A and B. But once again, this is a little tricky. 3.5 is only this much, which was a radius. This is also a radius, so that's another 3.5, meaning this whole side is really 7. So we're going to do x squared equals 7 squared plus 6.4 squared. So when I use my calculator to do 7 squared plus 6.4 squared, I get x squared equals 89.96. And when I take the square root of both sides, x is 9.5. So there's a check-in here. You can pause. Answers are posted on Google Classroom. So there's a few more properties of tangent lines. The first one being what I like to call the ice cream cone theorem. If two segments from the same external point, like point B, are both tangent to the circle, then they're congruent. I always imagine it that if you were to have an ice cream cone, the two sides of the cone should be the same height, otherwise your scoop of ice cream would fall out. If you had one side like this and one side like this, that scoop of ice cream is not going to last very long and it's going to fall out of your cone. So the two sides of the cone must be exactly the same to hold up your scoop of ice cream. The second one says if a polygon is circumscribed around a circle, then all sides are tangent, which would mean we have multiple cones. That would be one cone, which those two pieces are the same. This would be a different cone, where those two pieces would be the same. And this one would be a third and different cone, where these two pieces are the same. So we're not going to say the two on the same side like this are equal. We're going to say the two that meet at that external point are equal. So for example 5, if these are both tangent, then they're equal to each other. So I can set 8x minus 19 equal to 5x plus 23. Take away 5x. Add 19. and divide by 3, and we get x is 14. And they're asking me to find AB, so we'll plug it back in here. So 5 times 14 plus 23, 70 plus 23, so AB would equal 93. And I probably should just double check my math on this stuff. I think we're good. So here's a check-in for you to try. Pause. Answers are posted on Google Classroom. For example 6, we want to find the perimeter of this quadrilateral. So I'm going to start where I know small numbers. I know this little piece here is 23. So if I meet it at the other side, this little piece here is also 23. And the same thing, this one is 27.1, so the piece that meets at it would also be 27.1. What I can do is if this whole side of PQ was 37.5, and I knew part of it was 23, if I subtract them, I get 14.5 for this little piece, which will match on the other side to be another 14.5. And the same thing on this side. If I took that 52.5 and took away the 27.1, I would get 25.4. So now these two should be the same, so that's another 25.4. When I do my problem like this, I'm going to now ignore any of the big side numbers. They've served their purpose to give me the little pieces, and now they're done. To find the perimeter, I'm going to add up all of the little pieces. And because there's 2 of every single number, what I like to show is 2 times, and now I'll add up 1 of each. I had a 14.5, I had a 27.1, I had a 25.4, and I had a 23. So this is going to be 2 times all of that added up, which was 90. So 2 times 90, my perimeter would have been 180. So here's a check-in for you to try. Pause. Answers are posted on Google Classroom. We do have one last problem that we'll do together. It says find SV if both ST and SU are tangent to circle V. So knowing that they're both tangent tells us that they're equal. So we're going to say 10x minus 41 is equal to 4x plus 7. Take away our 4x, add our 41, and divide by 6. So we found x is 8. What we want is SV. There was no x value there for me to plug x into. But what I do have is a triangle here. And because ST was tangent, that means at the point of tangency, point T, there'd be a right angle. And if I'm looking for this side here, which I'll call Y because I already had an X in the problem, I know I could do Pythagorean theorem to find it. So I'm going to plug the X that I got back in here. So 10 times 8 minus 41. So 80 minus 41, we get 39. So I can do Pythagorean theorem to say y squared equals 39 squared plus 17 squared. So that's going to be y squared equals 1810. And when I take the square root of both sides, instead of writing y, I'm going to write SV now. So SV was equal to 42.5. And that is the end of section 10.1.